Hello everyone, my name is Ajay Medde from Aeronautical Engineering. In this presentation, I am going to discuss about my concept video in gas dynamics, which I took a topic on speed of sound and Mach number. Now we will see about what is meant by speed of sound and we will derive it from scratch. Speed of sound, acoustic speed. We now look at the changing conditions imposed on individual gas particles as the pressure pulses passes. As first simple approach to defining the pulse and its speed of propagation, we consider the steam tube's velocity to be such that pulse is stationary. The flow upstream of the pulse has velocity u, density rho and pressure p, whereas the exit flow has these quantities changed by infinitesimal amounts of u plus dou u, comma, rho plus rho dou and p plus rho p. Now we will see the figure and let's understand clearly. This is the figure whereas the figure A showing that stationary wave and it is going through a duct where the velocity u, and after that it has become u plus dou u. Now you can see in moving wave, whereas u becomes 0 and it is going oppositely, the speed is going oppositely and it is going dou u. The flow is now quasi steady, assumed inviscid and adiabatic, since the very small pressure changes takes place too rapidly for heat transfer to be significant. It takes place in the absence of external forces and is one-dimensional, so that the differential equation of continuity and motion are respectively u dou rho dou x plus rho dou u dou x equal to 0 and u dou x equal to -1 rho dou p dou x. Eliminating dou u by dou x from these equations leaves u to dou p dou rho, which implies that the speed of flow in the steam tube required to maintain a stationary pulse of weak strength is uniquely the speed given by rho dou p by dou rho. The problem is essentially unaltered if the pulse advances at speed u is equal to dou rho by dou p through stationary gas, and since this is the ideal model of the propagation of weak pressure disturbance that are commonly sensed as sound, the unique speed dou p by dou rho is referred as the acoustic speed A when the pressure density relation is isentropic as assumed previously. This velocity becomes A is equal to dou p dou rho equal to rho p rho. Recalling that is the speed of the gas attains in the throat of a choked steam tube, and it follows that weak pressure disturbance do not propagate upstream into a flow where the velocity is greater than speed of sound, that is u greater than a or Mach number m greater than 1. For the usual case of air being an ideal gas, becomes A is equal to rho RT. This is the equation for speed of sound. Now we will see about what is meant by Mach number. Mach number. Mach number is a dimensionless quantity in fluid dynamics, representing the ratio of flow velocity past a boundary to the local speed of sound. It is named after the Moravian physicist and philosopher Hendrik Mach, where m is the local Mach number, u is the local flow velocity with respect to the boundaries, either internal such as an object immersed in the flow or external like a channel, and c is the speed of sound in the medium, which in air varies with the square root of the thermodynamic temperature. Subsonic condition occur for Mach number is less than 1, m less than 1 for the lowest subsonic conditions. Compressibility can be ignored. As the speed of the object approaches the speed of sound, the flight Mach number is nearly equal to 1. Mach equal to 1 and the flow is said to be transonic. At some places on the object, the local speed exceeds the speed of sound. Compressibility effects are more important in transonic flows and lead to early belief in a sound barrier. Flight faster than sound was thought to be impossible. In fact, the sound barrier was only an increase in the drag near sonic condition because of compressibility effects. Because of the high drag associated with compressibility effects, aircraft do not cruise near Mach 1. Supersonic conditions occur for Mach number greater than 1, less than 3. Compressibility effects are important for subsonic aircraft, and shock waves are generated by the surface of the object. For high supersonic speeds, 3 less than m less than 5, aerodynamic heating also becomes very important for aircraft design. For speeds greater than 5 times the speed of sound, Mach number greater than 5, the flow is said to be hypersonic. At these speeds, some of the energy of the object now goes into exiting the chemical bonds which hold together the nitrogen and oxygen molecules of air. At hypersonic speeds, the chemistry of the air must be considered when determining forces on the object. The space shuttle re-enters the atmosphere at high aerodynamic speed, Mach greater than 25. Under these conditions, the heated air becomes an ionized plasma of glass and the spacecraft must be insulated from the high temperatures. Yeah, here it is showing that what is meant by Mach number. It is a ratio of object speed by speed of sound, and here we see that the aircrafts which runs in subsonic, Mach number less than, and transonic where Mach number equal to 1, and where supersonic is greater than 1, and hypersonic vehicles which goes in greater than 5 Mach number. Thanks for watching.